I may welcome all the interested listeners to my presentation of a machine learning model for the determination of macroscale masonry properties based on a virtual laboratory at microscale. This publication has been elaborated by me, by Luca, Pelà, and by Ricardo, Rossi, and we are all working and researchers at the UPC here in Barcelona. Before starting, I would like to outline my research. I will give a short motivation why I'm working on machine learning models for the determination of material properties for masonry. Then I will explain my methodology, and after having done this, I will show you some application examples, and in the end we are going to conclude this research. So let's start with the motivation. First of all, we are trying to find a masonry homogenization technique that is utilizing directly processed data for the macro model calibration of masonry structures, and it's basically used for numerical analysis. And while talking about numerical analysis in masonry, we have two different modeling techniques that have been elaborated in the last years. On the one hand, there's the micro-modeling technique. It is distinguishing between the material components. So we are numerically modeling the bricks and the mortar, and sometimes there are models that do also include interface element in between these two materials. The advantages of this method is that we do very accurately represent the crack mechanisms, but the drawback is that we have a high computational cost, and this limits us at the same time to the application of small-scale structures. So in parallel to the elaboration of this technique, there has been the macro modeling. Macro modeling is a completely different approach because it is smearing the heterogeneous material of the masonry in a homogeneous material. So this at the same time is reducing the computational cost, and it makes it acceptable. So we have the allowance to analyze large-scale masonry structures. Well, the drawback is that we have a complex material calibration, and it limits us while representing the damage of masonry. So there were some multi-scale techniques that were trying to combine these micro-modeling and macro-modeling approaches by, for example, first-order computational homogenization or by adaptive offline techniques. Both these techniques apply a hopping around at both these scales, at the micromodel scale and at the macromodel scale during the analysis. So it's still not so effective when you want to apply it to large-scale structures. That is why we have the approach of using directly processed data and machine learning for such a so-called multi-scale technique. And let's start with the methodology and with the idea. So as we explained, we are trying to combine micro-modeling and macro-modeling with machine learning. So on the one hand, we have this somehow micro-model looking part. On the other hand, we have the macro-model part where we are able to analyze large-scale structures. And both are connected by a machine learning, which is giving us a constitutive law on the macro-scale level. So first of all, we need to define this constitutive law. We are using a strain equivalent model with the damage parameters D plus and D minus, where we are splitting the stress tensor, and in order to have different material behaviors. And then we are applying a yield criteria, which is really advanced for masonry. It has been shown by Petraka et al. In 2016. He's using a Lubliner modified approach, and then we are using a damage evolution laws for the D plus and D minus, which are really advanced. In this case, we have parabolic curves for compression and tension behavior. And now we can jump over to the machine learning model, which in this case is a supervised one. This means that we are going to define a mathematical model that depends on parameters, and then we can go to this model and train the model with coupled input and output pairs by minimizing a predefined loss function. And the model we were explaining before, like the constitutive law, fits perfectly into this condition because we have a law that depends on strains and on parameters, which are, like, for example, the tension strength, compression strength, or the fracture energies. And then the output is a sigma. So we have these two we have an input, which is the strains, and an output, which is the sigma. And with this data set, we can perfectly train parameters. And that is what we are going to do. I've been using a Python API, which is called TensorFlow, which is made by Google. And here we can perfectly compute or define such a computation graph. So in the center, we have the constitutive law. Into the center constitutive law, we are feeding the parameters and we are feeding the strains from this placeholder part. And then with these strains and the parameters, we are going to compute a predicted output. This predicted output goes to a loss function and compares the predicted stresses with the ones coming from the placeholders, from the data set we are having. So both these stresses we are comparing and we are optimizing the values so that the difference between, so that the loss between these two stresses is reaching a minimum. And when we have reached the minimum, we have a perfect constellation of our parameters. So, but the question is, how are we going to train this model? So we need to feed our placeholders with strains and stresses, and that is how we are going to produce. Therefore, we are going over to the virtual laboratory. In the virtual laboratory, it's a virtual space for data production. There, we are going to define a representative volume element at the micro model scale. So we are distinguishing between the bricks and the mortar. And on this RVE, we are going to execute an arbitrary number of virtual experiments by applying different boundary conditions. So each case has a different boundary condition, as we can see here for example, 4 cases. And we have different deformations, and yeah, this leads to different stresses and different strains. And these coupled strains and stresses we are storing in a huge file. And with this data, we can go to the training of the machine. So as I've shown you, so I've explained the virtual laboratory, which is at the micro modeling stage, and I've explained the machine learning model and the constitutive law, which is later going to be used at a macro model scale of analysis as a post-constitutive law. So now we are going to explain this procedure on 2 application examples in order to make it clearer to the audience. So the first example I'm going to show you is a Flemish masonry bond. Therefore, we have calibrated a micromodel RVE, we have performed the virtual laboratory, and we have trained the machine learning model. And in the last step, we must somehow evaluate the machine learning trained constitutive model, let's say. So with the calibration, basically this is a classical calibration. So what we've been doing, we had this inside our group at UPC, we have tested this masonry wall in the laboratory, and we took the experimental data and built up a micromodel RVE, a numerical model, and ran a nonlinear analysis in order to obtain these curves. So by modifying all these data and the parameters of the law for the bricks and the mortar, we have, by trial and error, we found this perfect fitting curve and a constellation of the material data in order to have a calibrated micromodel RVE. So with this model and the material properties, we constructed the RVE, which in this case has an edge size of around 0.5 meter. And on this boundary, on this RVE, we've applied 26 different boundary deformations. So we ran nonlinear analysis, in total 26, until failure. And this procedure has been implemented by me to a Python script and is completely automatic and can be performed for more and for less cases also. So this is what comes out of this analysis. We have damage plots here. We can see for all the 26 cases a different crack pattern, and yeah, this generates us a large data set of coupled strain and stress states. And in particular, we have for each case and each step of each case, we have all the data stored. So we are obtaining a huge file with strain and stress pairs. And the nice thing about this is that the data includes linear and non-linear material data. So it's perfect for training our model. So this is the next step. We can go over to the training of the machine learning model. And here you can see in the table the the material properties of our constitutive law and tension and compression, so we need to train these data. Therefore, we input our training set into the machine learning model, and after each step of training we are randomizing the constellation of the input data. Then it's basically a very implicit optimization procedure of the parameters until we reach the predefined loss, and then we have a final parameter constellation which we can also like validate somehow by comparing the input with the output. And like as we can see here, the training set is giving us some black curves, and for 4 cases we've shown it here, and we are like generating with the optimized parameters, we are generating the curves, and we see that there's a quite good fitting in between them. So then we have to evaluate this training model. How are we doing this? So what I did is I ran 2 different cases, which the one is a compression case and the other is a shear compression case, and each case I've been modeling on the one hand as a micro model and on the other hand as a macro model. So the micro model is considering the material properties we have previously calibrated, and the macro model is using the material law of the machine learning model. So we have in total 4 analyses. Yes, and when we start to compare the results of the micro model and the macro model, we can see we are showing here on the one hand for the compression test, the reaction force versus the vertical top displacement, and for the shear compression test we are showing the reaction force and the horizontal top displacement. And and we can see also the principal strain, the maximum principal strain, and the displacement at an ultimate stage of the analysis. And we see very accurate results. Then I would like to step over to another application example, which is a large-scale masonry structure. It is called the Palacio Pereira. It was built in 1872 in Santiago de Chile, and it suffered from several earthquakes in its history. And well, it's a reference example for irregular masonry structures exposed to seismic action. So it makes it really interesting for this type of analysis. And what we are doing here, we are applying the machine learning homogenization technique in order to analyze a facade of this building, which in this case is a 2D nonlinear pushover analysis. I would now like to show you some results of this analysis. So on the one hand, we've been applying a conventional calibration of the macro model. Therefore, we have built up a model in the Diana software, and we ran the nonlinear pushover analysis there. And on the other hand, we used the open source software Kratos Multiphysics developed at the UPC, because there we have the machine learning trained constitutive model implemented. So you can see here on top of both of these crack patterns, of the displacement patterns at an ultimate stage, you can see the cracks. The one on top is from the Kratos analysis, so from the machine learning approach, and then the other one is from the Diana approach. What we can see basically is that we have a difference in the linear behavior due to the material orthotropy of masonry, which is considered in our machine learning law and not in the conventional one. And then we have a higher ultimate force load for the machine learning technique. So in the end, what is the conclusion of this research? So first of all, we have presented a machine learning based material homogenization technique, and at the same time we have elaborated a virtual laboratory instrument for numerical data production. And then we have invented our technique in order to apply it to on the one hand, a flemish bond masonry wall. There we've seen that our results are in very good agreement with those obtained from micromodel analysis. And at a second stage of application, we have applied the technique to a large-scale masonry building, a historical one. There we have seen that the conventional approach is on the safe side, but it only considers a single calibration example, and this is not done by our machine learning model, because there we consider a bigger amount of calibration examples. And in the end, I would like to thank the Spanish government and the Generalitat de Catalunya for the research funds, and basically I I would also like to thank you for reaching the end of my presentation.